Hello, my name is Roshan Jadhav and I'm going to talk about molecular dynamics simulations on cloud computing and machine learning platforms. Problem definition. The problem with current molecular dynamics simulations is that they are often computationally expensive and require high performance computing infrastructure, such as supercomputers, which can be costly and difficult to access. Additionally, performing simulations for large sets of parameters to effectively explore the material design space can be time-consuming and costly. Cloud computing and machine learning platforms are a potential solution to these problems. However, there are still challenges to be addressed in order to leverage these platforms effectively for MD simulations. For example, the high volume of data generated by MD simulations can be difficult to manage and analyze efficiently in cloud environments. Additionally, there may be challenges in optimizing the performance of MD simulations on cloud computing and ML platforms. Therefore, the problem definition is how to effectively perform MD simulations on cloud computing and ML platforms in a cost-effective and efficient manner, while also addressing challenges related to the data management and optimization of performance. Scientific introduction. Scientific computing applications such as molecular dynamics simulations are important for understanding natural and synthetic processes. MD simulations are used to explore the design space associated with material attributes and establish links between design parameters and material response. This approach is also central to using ML to enhance MD simulations and expedite the exploitation of the material design space. Large collections of jobs with independent parameter sets are launched to train and test ML models designed to enhance the predictive power or reduce the computational costs of MD simulations. As the utility of MD simulations are their ML enhanced versions in the rational design of material is further demonstrated, it will be necessary to leverage diverse advanced cyber infrastructure platforms to perform low-cost simulations. Blur dynamics on cloud platforms. Problem. The large-scale molecular dynamic simulations are required to significantly computing resources while are traditionally provided by high-performance computing infrastructure. However, cloud computing platforms are increasingly being used to supplement HPC infrastructure due to their on-demand resource allocations and cost effectiveness. However, deploying simulations on cloud platforms present unique challenges such as cost optimization, frequent job failures, and server configuration heterogeneity. S- For this, SpicePod solution is given. SpicePod solution is a framework that optimizes the deployment of scientific computing applications on transient cloud servers, specifically Google preemptible virtual machines. It uses an empirical and analytical model of transient server availability to predict expected running times and cost for different types and durations of jobs. The, by considering the entire bag of jobs as an execution unit, SkySpot enables simple and powerful policies for optimizing cost, make span and ease of development. Its cost minimizing server selection and job scheduling policies can reduce cost by up to 5x compared to conventional cloud deployment. The use of SpicePods can enable low-cost MD simulations on cloud computing platforms. Advantages of ML systems for executing and integrating MD simulations. Molecular dynamics simulations are typically coded in C, C++, and parallelized using OpenMP and MPI, but more modern MD software packages like HOMD Blue have demonstrated that MD simulations can be easily written in high-level languages such as Python. ML platforms such as TensorFlow offer automatic parallelization of simulations, enabling high-performance simulations and seamless use of next-generation cloud and HPC hardware like GPUs and TPUs. ML system offers extensive support for debugging, data analytics, and post-processing tasks that can be leveraged to perform all simulation-related tasks at a single platform. Developers have access to much bigger data science and ML community and associated tools that are richer and are actively developed and improved. Users and developers can easily share all simulation models and methods in one notebook that can be run on an ML system backend such as Google Colab, ensuring reproducibility, and ease of sharing. Data operations in ML systems are first-class operations instead of being a separate stage of the simulation workflow, allowing for better integration with data-driven approaches. Expediting material design space exploration through ML surrogates. ML surrogates are models trained on data for MD simulations that are used to approximate the relation between the input parameters and the simulation outcomes. ML surrogates offers a faster way to explore the material design space, bypassing parts or all of the explicit evaluation of the simulated components. For instance, the ML surrogate in 12 can reduce the interference time for 30 minutes to 0.2 seconds, 10,000x speed up. The surrogate model in 12 can be trained using a bag of jobs of size n is equal to 6,000 each job, representing a unique set of parameters and discretizing the high-dimensional input design space. The seamless integration of simulations and data-driven models on a single platform offers many opportunities for a rational and exploration of the material design space. ML surrogates are just one example of how ML systems can enhance MD simulation and expedite the material design space exploration. Integration of machine learning systems for rapid material design space exploration. Machine learning systems can be used to execute molecular dynamics simulation and integrate them with data-driven models. Advantages of using ML systems for MD simulation include automatic parallelization, extensive support for debugging and post-processing, and a large community of software engineers. The integration of simulation and data-driven models offer opportunity for a rational and expedited exploration of the material design space. ML surrogates trained on data from MD simulations can be used to estimate input and output relation and enable a rapid transition from simulation to surrogate. Opportunities of integrated approaches include unified execution of simulations and training of ML models, on-the-fly development of surrogates, improved surrogate accuracy and interference times, and effectively new simulations code development. Open questions and future directions. ML-assisted MD simulation require advances in cloud resource allocation such as abstraction and rethinking performance metrics. ML platforms can provide a unified framework for future applications that will integrate ML and MD simulations in a new way. New performance optimization and abstractions are necessary to handle natural performance challenges. Bringing MD simulations into an entirely new cloud plus ML ecosystem will require the HPC, cloud, and ML communities to work together with domain scientists and engineers. This confluence presents opportunity for the next generation of domain scientists to be trained in practical ML and cloud skills. Conclusion. In conclusion, the integration of cloud computing and machine learning platforms with molecular dynamics simulation presents exciting opportunity for advancing materials science research, enabling more effective, efficient exploration of the design space and improving the accuracy and speed of the simulation. However, it also poses unique challenges requiring novel abstraction, performance metrics, and collaboration across research communities. With continued innovation and collaboration, this convergence of technology has the potential to unlock new scientist discoveries and accelerate the development of materials with desirable properties. Thank you.